Actually, we swapped the tomorrow's session and today's session. Okay, due to some restrictions, we are going to do the experimentation for both the programs. We are physically create the file for path planning as well as what design we wanted to print for tomorrow's, and how to create STL file, how printing is going to be taking place in PBF process and as well as in the WAM process, and some post processing also we'll see in the tomorrow's afternoon, and we'll go to lab. But today we are going to learn regarding this end topology software, how we are using to reduce the weight of the component in all the aspects, either in the medical aspects or in the aerospace aspect, or as well as in the automotive aspects, or even in the fashion designing aspects. Why we require this minimizing the weight? As we know already, to improve the efficiency of the engines, either the aircraft engines, or to improve its performance by reducing the weight of the component, by maintaining same factor of safety, to maintain the weight, and as well as to change the material properties, or we can replace some other materials to maintain and as well as to reduce the cost of manufacturing. How efficiently we can use this end topology to redesign the existing old component which is suitable for IT manufacturing process, because we are already doing conventional manufacturing process. Their application of this topological design is challenging issues, because we do not have that such kind of machining aspects. Because if you want to see some of the topologically designs, curvilinear designs, where we are like providing a support structures for our fabrication aspect, such kind of supporting materials by machining conventionally, it is very hard. There was no facilities, because we need to go either non-conventional machining, or we need to go some kind of YDDM, or some kind of water jet machinings or laser machinings, and the such kind of process we need to use for those things. But still we have a restrictions, we need to create lot of fixtures for those things. But how we can overcome such kind of designs which can be adapted by IT manufacturing? That is what we need to understand by topological designs. But no need to just redesign it, but will it qualify the component? That component, can it be qualified for the applications? Simply with reducing the weight of the component is not going to suit for the application. But how we can make it suitable for the real applications, even after reducing the weight, changing the designs which is suitable for IT manufacturing process, and as well as suitable for our application orientation. That is what we will learn in this topological aspects. In the next session we will learn about this ABAQUS or ANSYS, how we can simulate this modeling aspects of our IT manufacturing process, PVF or LDD process. Okay, now our my student Srikanth is going to finish this topology. He is a PhD scholar. He has finished almost his work in this, and he submitted thesis. He is going to give how to train, how to do the topological aspects of IT manufacturing. Okay, thank you.
Reduction methods in topology optimization. And today we are going to see the weight reduction methods, how we can reduce the weight using, there was one software called which is end topology, that is advanced CAD software. Specifically it is like a how traditional CAD softwares are different, and what we are teaching, that is different actually. What is the difference we will see, and first we will see the weight reduction methods. And we all know, okay, 3 weight reduction methods are there. One weight reduction method you all know, what is that method? How to reduce the weight, something like that. No. Like we all know means like by seeing, like has a 10th class to 10th primary guy also know, like which is heavier, like there is a one question like 1 kg steel or 1 kg cotton, which is heavier? Both are same. Then 1 kg steel or 1 kg or aluminum, which is heavier? Both are same, right? Like aluminum we have seen, right? Suppose you have a steel and aluminum is there, and you like volume is there, like 10 mm by 10 mm steel is there, and 10 mm by 10 mm by 10 mm aluminum cube is there. If you are lifting the same thing, aluminum is lighter, right? That is called, that we call the material. Like by replacing steel with material, we call it as a lightweight material. That we call it as a lightweight material. And one method is the material substitution. Like by replacing the material with the lightweight materials, like aluminum, titanium, we call that as a material substitution. And the second method is called the structural optimization. In that structural optimization also 3 types of optimization is there: topology, shape and size optimization. Mainly like people are focusing on the topology optimization. Right now the current trend is going on the topology optimization, that we will see, I will tell you. And the third one is the lattice structures. Lattice structure means this is not a new term to us, this is like a, and the even topology optimization also very new to us, I will tell you the difference. And the lattice structure means we have heard about the lattice, forget about the structure or something. Lattice, where we heard about the lattice? No. Like in nature we have had, like in chemistry we have had, right? Crystal structure. In chemistry we have had BCC lattice structure, BCC crystal structure, same thing, FCC, same thing. The inspiration got from there only actually. We are getting the inspiration, the lattice structure there only. And we will see that how the lattice structure get inspired also. And the classification of the lattice structure we can see strut, TPMS, planar, we will see the difference between all these things. And we take quick slides. And this is a material substitution, this is the old like during old method, old method, it does not mean that we cannot use right now, we can use, but previously long back we are using the material substitution. Currently people are using the structural optimization, and in future like maybe in space or some in SpaceX or NASA, these people may use a lattice structures also to reduce the weight of the component and improve the efficiency also. And for this is the weight reduction, right? Why we need weight reduction actually in general? Take an example and why we need the weight reduction. Take any example. Forget about the aerospace or automotive, forget about it. If you know any example, you just quote an example to me so that I just want to.
Let us take a passenger car or protocol. We want to reduce the metal sheet thickness. Then as you said, weight will be reduced and fuel efficiency will be improved.
Yeah, fuel efficiency will improve. As he said that if I like car, he said right, automobile, right? In aerospace there is one problem is that, I mean whoever is traveled in the flight they might know this thing. Actually in aerospace there is a problem with the fuel consumption, because in between air, for like in automobile in road only we can fill the air, but in between air we cannot fill the air, right? So what they will do means they will calculate each and everything, they will calculate each and every weight, like they during the check-ins also the luggage is there, overweight is there, they will send it to some other way, and if they ask overweight is there, we need to reduce the weight and all those things, like check-ins is there happen, right? Why they are doing this means just to check this, just to fill the fuel only actually. So in between we cannot fill the fuel, right? So aerospace 1 gram of reducing the 1 gram of weight also very important, like it will improve the fuel efficiency also, that fuel cost also very high actually. So that's why we are getting a like flight tickets are very high because of this, and they are reducing the weight constraints are there actually. And the factor of safety there, just remember that in buses we are getting a factor of safety, like factor of safety is there is no extra passenger, something like that. Whoever the passengers are there, that will be fixed actually, there is no vacant of the passenger are there. That is the factor of safety. Aerospace is 1 actually, they should strictly follow, there is no like no not 1, like some 10 or something like that. But in buses or something factor of safety you can go for 0.8 also, like we are going beyond the limitation of the passengers, right? That will be, but in aerospace they will take the huge number of factor of safety. So the structure should be very high strength to weight ratio. So that is the future, and these are some of the lightweight materials. But the first one is the past one is the lightweight materials. Right now people are using aluminum alloys, like shootable AM process also we can see, and where we are using the aluminum, mainly titanium alloys we are using the aerospace and medical implants actually. And this is the shootable AM process, you can see it. And the composites, polymers, ceramics, these are the lightweight materials, and the shootable AM process also we can see, okay. And this is I told you, right, aerospace and automobile body, this is the composites we have seen, steel, aluminum, steel and plastics they are replacing just to reduce the weight. This is how the car body is designed, and this is how the material get replaced, okay. Yeah, the question is that I told you the topology optimization, right? There is one more like one side of coin topology optimization is there, and the other side of the coin generative design is there. Mainly people means designers who are working on it, they are getting confusion. Let me clarify that generative design and topology optimization are like a apple and oranges, not like apple and apple, okay. Both are not same, means both are like a different, okay, but they both are on the two sides of the coin, okay. So what is the meaning of the first? We will go for the topology optimization. It will be very interesting, like you know this thing actually, like don't combine the two words, like separate the two words so that you will get the definition, okay. like one is like a topology, other is like a optimization. So what is the meaning of topology?
properties of nature of surface.
Surface, okay, like in terms of design it is there actually.
The features of a surface.
Surface is okay, like okay, I will tell you, topology means geometry actually. As a design in it, like topology means we like yeah, topology means geometry, and the optimization means okay, why we need we this one we have had optimization. Like you are not optimistic person, we like that we are had about this thing, right? And the optimization also we have had. There is one term called, whether you know or not, SEO. How many of you know SEO? SEO, search engine optimization. Have you heard about it? Yeah, search engine optimization means, okay, then what is optimization there? Optimization. We might have heard and thought this thing. Why, how they will proceed means, they suppose you are searching one product or something, you are searching something like what we call something, you are searching a product means it will give you the best results actually. The unnecessary results it will avoid it actually. So that we call it as search engine optimization. That should be SEO engines should be there actually there. So finding the best, and we suppose in short example, if I say this means finding the best means, in Flipkart you might have seen the, okay, optimization will go it, then what we will see. Optimization means finding the best. Your objective is to, suppose in Flipkart your objective is to buy a laptop or the mobile. So you need a specifications, your objective is to buy a mobile, okay. So you have the specification of your objective is the buying a mobile, and the constraint is that you have the cost constraint is there, and the RAM and the like color and these things are there. So that we are fixing the constraint, means filters we are fixing, and the objective is the giving the mobile. Suppose if you are searching a mobile and it won't give you the laptop, right? It won't give the results of the laptop, right? We are searching a mobile, right? So the filter we can do, that is the constraint we are doing, so that it will give you the finding, it will give the best results, so that we can choose one, right? Same thing will work on the topology optimization also. Same thing means our aim is to, our objective is to reduce the weight, and means reduce the weight, not only reduce the weight, we can reduce the weight at any possibilities, but improve the strength to weight ratio. Our objective is to improve the strength to weight ratio by using some constraint. That constraint may be, it should not exceed the factor of safety. Mainly factor of safety should not exceed more than 2. If it is exceeding more than 2, we can reject the sample like that. So it should not exceed factor of safety, means yield strength. It should not go beyond the yield strength, like that. These are the constraints. And the deflection, it should not deflect, the optimizer geometry should not deflect. These are the constraints we are fixing, okay. So that we call it topology optimization, and the generative design will also work for the same thing. Objective constraint will give the best result, but the problem with the generative design means, you might have heard the design, but again separate the two terms. We might have heard the generative also. Recently this term is got popular actually, generative. Have you heard about it? No, generative term is recently popular right now. Yeah, chat GPT, right? Generative AI. What it will do? Generative AI means, like we are entering some prompt or text we are entering, it will generate the text, whether it is correct or not, that is our concern. But AI, it will works on the artificial intelligence, right? Like we are entering a prompt and it will generate some information, answer. The same thing will work here. Generative design also will use the artificial intelligence program, and the topology optimization will use the mathematical algorithm. Means the software can be we are inserting with the mathematical algorithm inside it. In generative design, suppose like chat GPT is there, right? If the internet is not there, will be able to work on, will be able to get the information? No, right? Same thing will work for this also. Like it won't work on the offline actually. The software, I mean I forgot to say the software. Generative design will work, as per my information, generative design work for only in the Fusion 360 only. Autodesk Fusion 360, there is a education license is there, you will get it for 1 year. And the good thing is that after 2021, I think, we for education license we are getting unlimited cloud credits, so that we can generate any number of things, okay. In the topology optimization, there are huge like whatever the software, CAD software we have, all work for the topology optimization only. Only one software that is working on the generative, means artificial intelligence using this generative vision, that is topology. So clear, right, the difference? Now the person got this, that was the confusion is there. So difference between that. Okay, we will see some of the examples, and you can, I mean, right now you may not identify the examples of the which is generative and topology, but once you go through the software, then you will able to identify. Once you see, you will able to identify. This is some of the examples, real time examples where we are using. See, this is the nature, like we structures, we all get inspired from the nature, right? Like I said, lattice structures, crystal, BCC, these things. Same thing. This, yeah, forgot. Like sometimes, like we are optimizing the material, means optimizing the, here on for the time sake I am saying, optimizing the material, sometimes for the aesthetic purpose also. The main motto is it should serve the purpose. Like the thing is, suppose you are sitting in a chair, right? The chair will be like this, but if I remove somewhere in the material which are not necessary, I can lift easily, right? So that I can lift the weight, but it should serve the purpose, like you need to sit comfortably, right? The thing is, it should serve the purpose. The performance is useful in the aerospace and automotive. There it should not serve the purpose, it should serve the purpose, it should improve the performance, okay? That was we are getting inspiration from nature only, okay? Yeah, what is this bike? Yeah, everyone know, right? Because of the color orange and black, okay? That is that structure is there, right? That we call it as a topology optimized structure. The material, we are previously, like I don't know about it, like but the structure is we are removing the material inside, that we call it as a topology optimization. This you don't know. I mean, this was, I think, 1 month back. They have recently implemented in the Ferrari car, actually. Ferrari F80 sports car. They have implemented. They have 3D printed this. This is suspension system. Like this is a topology optimized suspension system. I told you, right, it will just improve the fuel efficiency and all those things. Ferrari F80 car, yeah. And this one, bike name, I think logo you can see, maybe. Royal Enfield. No. This is a recent bike only. Recently in Delhi Auto Expo, they put it. No. This is electric bike. Royal Enfield electric bike, Flia. Royal Enfield electric bike, and the structure you have seen, right? This one. That we call that was optimized actually. And here also that design is there, right? Maybe because of the brightness you might not see. Here you can see. That was optimized, topology optimized, so that to reduce the weight only. And this one, chair, furniture, right? That was generative design actually. That is not topology optimized, that is generative design. As I am working on it, so that I can able to recognize which is generative, which is topology. And this one, generative. I told you, right, that should serve the purpose, be it strength or forgettable, that should serve the purpose. Here it is serving the, like sometimes like aesthetic purpose, like looking wise it should be good, like that, generative design, okay? Yeah, that one. And what is this, like some generative design is there, right? I look forward in time and saw the 14 like some futures we have seen, like Dr. Strange told to Tom Cruise, right? Sorry, Iron Man, right? So CAD engineer will, the same thing will work for the generative and topology optimization also. I will show you the example so that you will come to know. See, the original design is this one, and what it will do means generative and topology optimization, the algorithm may be different, but the thing is, the purpose of this thing is same. There we call it as a number of iterations, we call it as a, till it get converged. Number of iterations is there, right? 1, 2, 3, 4. Here due to the space limit we have shown 4, but it may give the some thousands of designs also. It will generate actually thousands of designs, so that we can finalize one design. Whether that is satisfied or not, in that software it will automatically give the table and chart, it will automatically give. We can able to select whether we can choose this design or not. And this is a sitting chair, we can see original design is there, like we are that should serve the purpose. This type of designs is already existed, like we are seeing the table chair and all those things, right? So how many possibilities we are getting means only one we are getting, only one we can choose, the best one we are getting, the only one, okay, till it get converged, okay. So the next thing, okay, next thing is lattice structures. So lattice structure means What is the meaning of lattice? Okay, forget about the lattice. Is say okay, I can say porous structures. Lattice you might get confused. Porous structure means some pores, holes should be there. Okay, hole type of structure, material removal. Okay, so what is okay? You got inspiration. I told you right, like BCC and all those. There are some other things also there that we will see in the inspiration where we get inspired. Like okay, first of all, what is the meaning of unit cell? In lattice structure, like suppose he might have see the Rubik's cube, right? How many cubes are there like that? Rubik's cube. We are playing with the Rubik's cube, right? Different color Rubik's cube. There may be 3 by 3 by 3 or also 4 by 4 by 4 also Rubik's cube is there, right? Means 64. That one cube we are extracting, right? That we call it as a lattice structure. That is repeating, right? And you can see here holes is there, right? Holes. That is repeating, right? Like x, y, here this is the 2D holes. Like x, y, z it is repeating. The same hole is repeating, right? The same thing. Rubik's cube also the same size of cube is repeating in the x, y, z direction. That one piece of unit is there, right? One piece of unit. Like in derivatives we have seen, right? Suppose if you want to calculate the area of the surface or something, we are taking a one piece and we are integrating. The small piece we are integrating. That one piece is called it as a unit cell, and we are calculating that one piece into like that. Okay. If we see that, then we will come to know in the end of software this is there. And why we are going for the weight reduction means aerospace alarm due to reduce the fuel consumption. In biomedical also it is there actually. Why? Why like I will tell you the example. This may be the good or bad. Like some people know, like we are using some legs prosthetics is there, right? Prosthetic in olden days some legs is there, I think so. I mean I don't know. We call it as a Jaipur leg something. We call it as a. Is it still there? That is the correct one. Jaipur leg only, right? I don't know why they call Jaipur leg, but they call Jaipur leg something like that.
Why it is called Jaipur is because the doctor who created that one, he is from Jaipur.
Okay, okay. So okay, it is familiar word only. Jaipur leg is familiar. Okay, okay. Because my father used to call like that. That's why.
Actress, even Bollywood, she uses that still.
Okay, okay, okay. Yeah, Jaipur like they are keeping this one, right? So that will be very heavier actually. Suppose if you are walking this means we can't able to bear our foot, right? That will be very heavier. There the weight reduction is very important. So what people are doing, biomedical engineers are doing, they are adapting the lattice structures. Like prosthetic arms they are designing actually, and some cement we are doing this thing, right? Like cement joint something like that, right? They are doing the prosthetic arms, and mainly biomedical implants they are applying this one. Biomedical implants how they are applying means that should match lattice structure. The good thing about the lattice structure means suppose we are getting a material aluminum we are printing, right? Aluminum the properties are same, stiffness, Young's modulus. Whatever you have designed that is aluminum, so the property is same. That will not change. But the good thing about the lattice structure means if I printed the different lattice structure, the property will vary. It won't depends on the material. You might have say like while studying the lattice structure, suppose if I printed the lattice structure with aluminum or some PLA material, we are getting the characterization, mechanical characterization we will do. The Young's modulus is there, right? The Young's modulus need not be same as the aluminum material because that is not a standard method. Standard method is the tensile specimen. So the Young's modulus is varying. The good thing is we are using this in the bones and all those things because that Young's modulus should match with the bone modulus is there, right? Because like that we are varying the properties and we can finalize it, which is good actually. There is a research is going on it actually in lattice structures, mainly in the biomedical bone, that we will see how to we will take that as an example, bone, and how we are designing with the lattice structure in NTOP. Okay. So this is the inspiration. How many of you recognize the first one? Which one? I think I have written the name. Okay. Okay, crystal structure. This one? This one? Yeah, fish is also correct example. Like there is one, I think in rapid prototyping, I think recently published, fish bone something, one type of structure they got inspired. That also right. So this is butterfly wings. And this one? Yeah, bone. If you cut like our bone is there, right? If you cut inside it, we can see this cross section. And the third one? Yeah, architecture. Can you rename other example than this, like this is like in ancient days they will build this type of architectures. Why they will put like this holes is there, the pattern is repeating, right? Why they are keeping just for the ventilation purpose? Because we cannot keep everything as a solid, right? There is no ventilation, right? So they will keep inside their repetition pattern, lattice structure, like porous structure, something like that. We are getting inspiration from there also. And one more thing is Eiffel Tower is there, right? That we call it as a, why not give, that can be a solid or something, like trusses is there, right? That, yeah, trusses is there, right? Why can't we keep it as a solid, just to ventilation purpose and to improve the strength and all those, okay? This is the geometry variation. You can see the geometry variation, how it is varying the, as I already told you, right? See, from bottom to top the structure get varied, it should not be same, okay? And you can see the, here in hexagonal the property is not changing, hexagonal, square and reentrant, it is not changing the cross section, means that is a 2D lattice, remaining are 3D lattices. And the bottom is, in bottom 4 is called as the TPMS lattices, okay? And the applications, I told you the example, right? Application of this one, aerospace or biomedical, defense, energy, these things. This is how we can use the applications. And this is some of the app which I did, like lattice structure applications. You can see the, all these things are the applications of the lattice structure where we can use in different categories like sports and fashion design and engineering, home appliances, these things, okay? So, yeah, this is the project which we did, lattice structure applications, and we should acknowledge them, like we, because of them we completed our, I mean specifically our research got completed very quickly because of the, they have provided something, we have explored these many applications and we found it should be interesting. So, I just want to share that, we shared that, okay. And this is about me. So, with this quick introduction we can go through it like NTOP software. You have a, you get a clarity about the lattice structure, right? Any doubt in it? Like anything, if no, if nothing is there, we can go for software, okay? So, you are able to see, right? Screen, black, dark mode I am using, okay? You are able to see, right? So, and this is the NTOP UI you can see here, and mainly we are using for the, as I told you, right? Just a quick glance about to NTOP I will say, like UI I cannot able to touch due to the stipulated time, like, but the main mode of the NTOP is just to design the weight reduction designs, and means topology optimization, be it a topology optimization, be it a lattice structures or anything. And the why NTOP with AM means, if you are working on the AM means and some good structures DFM or something, then you should familiar with this software, because there is a lot of opportunity, like in future I am saying, in future there is a lot of opportunity that can be explored in this software. This student license we are using, we got a student license, we are using that only, and for not for the commercial purpose, like we are using for our research purpose we are using. Yeah, if you want to explore the research purpose, you can apply for the license, they will activate it. In the website it is there, NTOP website it is there, you can apply for the license. We are using for the, not for the commercial means like selling or purpose or something, just for the research purpose only we are using. No, that is different, that is for generative design actually. This is different, this is for lattice structure and topology optimization. Yeah, Autodesk Fusion will be different, yeah, both are different, don't get confused, okay. NTOP means formerly known as Topology, now they are keeping the rename as a NTOP, okay. So, the main advantage of this means in additive manufacturing, they are like suppose additive manufacturing we are there, right. So, additive manufacturing print the complex structures, right, this will give you the complex structures, like organic shapes are there, right, organic shape, bionic shapes, that will, like in the beginning of the slide you have seen the example, right, that Ferrari, these things that we cannot able to manufacture with the subtractive methods. So, we are going for additive manufacturing, and the lattice structures also, that is very precise geometries is there, and there we cannot produce a die or something. So, we can complexity free geometries we can able to print with additive manufacturing, that complexity will take care of this NTOP, okay. So, we will take an example of the, I will tell you how to generate a lattice structure and the inside like the properties, mechanical property, that is again deviating from the research, that you can find it in the, like I will introduce about the software, how we can generate the lattice, okay. And I already told you the unit cell, all these things, right, that I will show you. Yeah, and one more thing, NTOP will work on the, I told you like traditional design, and there is a lot of difference between NTOP and traditional design, CAD design. In traditional CAD design like SolidWorks and Creo, what we are doing means we have a 3D model diagram is there. Here we cannot able to miss 2D sketches, we are getting a 3D models, right. But here it is not like that, there is no 2D sketches or something, okay. That is why there is no plane, front plane, top plane, these things. That is for the, this is here there, that is for viewing purpose only. That is not a plane or something, don't get confused, okay. So for 2D sketches we are using a planes, here there is no 2D sketches. Once we have a 3D model, we can play with the 3D models. 3D models means original models, I am saying. That original models we need to design in the SolidWorks software, okay. Be it a cube or something, cube, simple things we can get it, cube, a cylinder, these things, sphere we can get it, that we can get it here. But the like tensile dog bow specimen, that is the sketch should be involved, right, that we can design it in the SolidWorks software. So first I will tell you with the cube from this software, and later I will take the tensile specimen, and how we apply the tensile specimen on the what we call gauge length, that I had designed in the SolidWorks, and later if time permits we can go with the bone or some automobile application, brake pedal, where how we are applying, okay. And this is like a implicit body, it will take like suppose, I mean this is a laptop, suppose if you are working in the some high configuration system, the good thing about this software means like we are getting in SolidWorks BCC lattice structure, we can easily design in SolidWorks, you might have find the videos also. But the problem with the SolidWorks means one unit cell we will design it, and we are patterning into 3 directions. But the problem is that, what will the problem is that we face this problem, personally we face, that is why we are saying like the problem is it, we are repeating, right, the system configuration, the system like processing will be very slower, it may dead also. So we need to save it continuously, and the file size we are getting is very heavy, higher file size, like it may be exceed to GBs also, that if we give it to computer or some slicing software, it won't even take the software, we need a high end systems. That is the problem with the traditional CAD. But implicit models is not like that, implicit model there is no faces, selecting faces or something, we will take everything as a single body, okay. So with this we will go with the lattice structure. There are again 3 types of coordinate systems are there, like rectangular coordinate system, cylindrical coordinate system, and spherical coordinate system, right. We will use the rectangular coordinate system and we will generate the lattice structures, okay. See here see modeling and creating this, you can also explain like that, anyway I will use it here, okay. See lattices is there, right, lattices means we will use the rectangular coordinate system, you can see here rectangular, cylindrical and spherical coordinate system, the shape will change, okay. Spherical means we can use only for spherical, it is not like that, okay. So rectangular coordinate system, and it is asking, once I press the rectangular coordinate system lattice, rectangular lattice, it is asking the like optional, you just remove it, leave it, and empty means it is necessary, we need to keep something here there, okay. See volume, it is asking, volume means what is the volume, original design, okay, original design, that should be implicit body, not CAD body or something, CAD body it won't take, that symbol is there, right, icon, that is implicit body symbol, okay. So if you are getting a confusion or something means, okay, when you further we will go, okay, first method I will tell you how to recognize, since if you are a beginner in the NTOP, how to recognize means I will tell you the first method, later method I will tell you next, okay. If you are a beginner or something, the first method is that just long press on it, it will give you the available options here, it is giving available options, these many available options it is giving, right. Means this black, this green color indicates the all are the implicit bodies, okay, Boolean intersect or something, but we need a implicit body of the cube or sphere or something. So just type it here, okay, long, like double press on it so that you can see the available options, or otherwise just type what type of design we want, like cylinder or sphere, cube or something. Suppose I need a cube, I will press it here, will automatically give you the cube, see there it is giving cube, right. So what is the size of the cube you need, it is asking, means the cube position is in horizontal, origin I am not changing that, what is the size of the cube it is asking. So I will take a 30, okay, 30 cube. So this lattice size I will improve more because of the processing time get reduced. So I will take it as a 10, 10, 10. Let's see. Acha, tell me like unit cell size. Okay, okay. First, okay. Anyway, I didn't care. Okay, first we can see the unit cell. There are three types of unit cells are there. One is like a strut based. Strut based means BCC. All the strut means rod type structures is there, right? Rod strut. We call it as a strut. That rod is called strut. Okay. That we call it as BCC, FCC. These are all struts. We call it as a like that. And the other type is 2D lattices. 2D lattice means the cross section is same, that we will see, and the other type is TPMS. The good thing about the TPMS means it is of the easily printable structures, and the properties are higher for the TPMS structure. That is why if you find, I mean, as a researcher, if you know about it or not, if you find any journals or something, mainly people are working on the TPMS structure, because everyone well known that TPMS lattice structures have the better properties than the strut based. But it depends on the application also. If your application is like a strut based lattices, then you need to work on the strut based lattices. So, okay. So here I will show you the like strut based and few strut based lattices and this one. Okay. So graph units. See, I told you that the first method, double press on it, you will see the available options. Okay. So double press on, you will see the available options. So I will take this first one, graph unit cell. This one. So it is asking the unit cell, again empty, ribbon button is there, you can press the ribbon, so that you will see the available unit cells here. These are all like graph unit cell, means line diagram. With line diagrams we can generate. Like strut means lines only, right? That line we are giving a cross section. Again 2D hexagon means that line only, right? Line we are defining a cross section. Okay, same thing. So we will see the which one we body centric cubic lattice we will see. Okay, and how the body centric cubic lattice means, this is how lines I told you, right? Lines it is there. Okay. And we can see the implicit view to get better understand. Thickness we can vary. Okay. See, this is a body BCC, right? Agree, BCC, right? And FCC, how it will look? See, this is how FCC will look like. Okay. All the faces are centered here. See, and simple cubic, FCC, BCC. These only we studied in the chemistry, right? And the other types are there, octet columns, diamond, these things are also there, that we can also explore. See, why we are calling this diamond? This looks like a diamond, right? So we are calling this as a diamond structure. Okay, and so that is how we can see. Okay, and the thickness we need to give. Thickness means this strut I am varying here, right? So Acha, tell me, like in the 30 mm unit cell, I am keeping, sorry, 30 mm lattice size cube is there. I am keeping 10 mm, 10 mm, 10 mm by 10 mm by 10 mm unit cell. So how many unit cells are repeated there? Pattern, I mean pattern, you can say pattern. How many are repeating there? See, 30 is there, right? Each unit has 30 is there. Each section I am dividing into 10 mm on each direction. One direction 3, then other, what about other directions? What about Z? There is not X, Y, you said 3 into 3. What about Z? Z direction is also repeating, right? Like say, take a Rubik's cube only. Rubik's cube in a 3 by 3 by 3 by 3 is there, right? Each cube has a that one, right? So 3 into 3 into 3, 27, right? So that is all. Okay. So the thickness we are adding, and the porosity, I will tell you the meaning of the porosity. We will see. Like I already saw told, we can reduce the weight rate. How we will see that we will see. So the thickness we can keep it as a 3 mm. Just see how it will, how the structure look. See, and we can change this into BCC. Okay. See, this is a pattern, and each direction that one has a pattern. See, 3, 1, 2, 3, 3, 3. So 3 into 3 into 3, 27, right? 3 factorial. Sorry, 3 into 3 into 3, 27. Okay. Suppose the weight saving I will tell you how to do, then we can proceed. You just type it here, and remember that these are the in traditional design we might use like this, like we can go here and we can go here, right? But here only one thing we are using, I mean, as my personal experience, we are using it in the search option only. This is the search option. Like each option I don't know where it is. It may be some other tab. There are multiple tabs are there. In future the tabs added also, but each option I cannot able to find where it is. So I will use the, I know the term, so I can use it here. So weight I need to reduce, right? Weight, I mean how much weight is saved. So that we will see, okay. This is better. So weight saving, see this is weight saving, right? See, as already told you, porous structure or lattice structure can reduce the weight, but we need to know how much it is reducing and whether the strength is sufficient or not, that we can do for the analysis. That we can, that also we can do, okay. So the here it is asking two types of bodies, comparison purpose. So how much it is reducing weight means how we can compare with original design, only I can compare, right? What is the original design here? The cube. How much is the size of the cube? 30 mm. So the original design is the cube, right? What is the name of the cube? Okay, I can rename this cube, as you said, cube 30 mm, okay. Okay. So this, that cube has that original body has the name of cube 30 mm, okay. So the original body I will type it here, cube 30 mm, okay. It is giving, right, see. So I will press it. What is the light weighted body here? Light weighted body. Acha, say the name, you are able to see the name, right? BCC lattice structure, right? So that we can give a name then, lattice underscore 0, okay, I can give BCC or lattice 30 mm, okay. Okay. So this I can press it, light weighted body, lattice 30 mm, will calculate it, see, you are able to see, right, okay. 64 mm we are 64, almost 64% we have reduced the weight, okay. 64% we have reduced the 64% we have saved the material, means there is 36% material is remained there, okay. So how we can, how I can further refine the I mean how I can further reduce the weight of the structure, this cube, take another one means, no, say whatever you want, I need the answer, whatever the answer I do not mind actually. That is one example, good. Like suppose because I told you that the geometry is not same for every structure, I told you in the video, right. BCC need not be similar to FCC. Suppose if I take FCC, that may be, okay, we will see that only. CC, right, how much, this is 64, see, 58 there, means 42%. We are like material getting increasing, right, because of the struts are adding more, right. So there is, that is one type of method, like changing the structure. And the other type, the input parameters only you can see, 3 input parameters we are giving, one is like a structure and other is like a unit cell size we are giving, and the third one is the thickness we are giving, right. So these 3 input parameters only we can play with the 3 input parameters, these 3 only, okay. So what will happen, now say the type of the structure completed, then the other type, then you can say thickness, what, increase or decrease, then what will happen, as you already quoted the first example, automobile, right, the sheet thickness we can reduce, same thing, if we reduce the thickness, weight will increase, like weight will reduce, right, means less amount of material will be there, that also we can try then. This is 58, right, so we can keep 2 mm, see 78% we have reduced the weight, okay. So that also proved, right. So what will happen then, what is the other method, what is the other input parameter is there, size means what size, unit cell size, okay. What will happen, unit cell size increase or decrease, okay. If I decrease, what will happen, if you know the definition, then you will come to know that unit cell size 30 mm, okay, I will tell you this, okay, wait, I will tell you this, in a 30 mm lattice 10 by 10 by 10 I am repeating, so each direction has 3 unit cells. Suppose if I am keeping a 5 by 5 by 5, then how many unit cells I can get it, so there 27, right, 5 by 5 by 5, how many unit cells I will get it, no, in a 30 mm unit cell size, so 6 unit cells we are getting in each direction, 6 into 6 into 6, I think 216, right, okay, I am poor in mathematics, 216, right, okay. So 216 unit cells we are getting. So now tell me, which is preferable, like 216 keeping the 216 unit cells, or means it is like the structure get compacted, the unit cell we are reducing, the unit cell size we are reducing, it means that the pattern is repeating more, right. So like if I keeping a 10 unit cell this much of size, the unit cell size is increasing, it means pattern is very less, right. So what will happen if I increase the unit cell number of unit cells, what will happen if it is increasing? Number of unit cells we are increasing, that we will see, okay, anyway increase or decrease that we will see now. That we will see then. Oh sorry, number of unit cells we are increasing, we are reducing the weight, means the unit cell size I am decreasing, okay. Suppose if I am taking 666 or 555, see previously 78% we have ready, means only 22% material is remain, now 37% weight reduced, means 63% material is there, so weight we are increasing, we are repeating the number of unit cells, see the structure, how dense the structure is, okay. That is how we can calculate the structure. These three input parameters, like if you go through any research paper also, they will use these three input parameters. That is one type of structure, BCC. We will see other type of structure in some other design, not in design, okay. So you know how to apply the lattice structure for a cube body, right. Now we will see we will take the advantage of the SolidWorks CAD designs, okay. Like there I will use the other type of structure. So I can take this other section. So first I will import the CAD model, right. I can't able to draw the CAD models here, I told you, right. First I will import the CAD models, okay. There is option Control I to import. See here I already designed tensile specimen, I will use this, okay. I will close this. Okay. See, the thing is, if you are applying a lattice body here, means in the entire body, means what will happen? We are keep fixing these things, means we are fixing in these things in the grippings. Even though we are keep fixing the as a like as a mechanical engineer, we know that our main intention is on the gauge length, right, gauge length, right. So we are applying the lattice on the gauge length only. Anyway, we are fixing those things in the lattice body, right, that grippers, so that we can keep it as a solid, okay. So for that what I did means I separated this into three bodies, and one more thing, NTOP is all about the Boolean operations only. We might have heard this term Boolean operation, where we had there also, then sets, like mathematics, in 10th class mathematics we might have had the sets, union operation, subtract operation, intersect operation. Union means combining, subtracting means we are subtracting something from that body, original body. Intersecting means common body we are getting, what is the common in it, okay. That thing only, entropy is all about the Boolean operations only. If you know about the Boolean union, subtract, intersection, then you can easily play with entropy, this software actually, okay. So this one we are separating three bodies. Why we are separating these three bodies means our main intention is that we need to take this body only, apply the lattice structure. So we separated this in the three bodies in the SolidWorks software, okay. You can also do here also, that I will do in the bone method. Why I can't able to use the SolidWorks software, I will tell. So I can convert this into, like if you want to perform any operation, further operation, once you imported, you need to convert that into implicit body, then only you can perform any operation, okay. Like be it a lattice or be it analysis or anything, you need to first convert into implicit body. So I will convert this into implicit body. So first one I will convert this into implicit body, this I will rename it left, tensile left, or other middle, this one is the middle, right. I will keep this as a middle, and this one is the right. See previously, okay, I will show you one, what is the implicit body. I told you previously we are able to select the faces and lines, right, points, lines we are able to select it, right, but in implicit body we cannot able to select. I will show you that. See, I can't able to select, it is giving as the entire thing as a one body only, okay. We cannot able to select the lines or something, okay. In if you want to play anything in the phases or something, then you should have the, you should convert into that into CAD body, okay. Here my intention is that I need to apply the in the middle section, okay, lattice, this one I can apply later, okay, I will tell you that. So again same thing, lattice, rectangular lattice, I will drag this middle one, so my body is the middle one now, okay. And forgot to say, like NTOP can, you can see the compatible file formats here. These are the compatible file formats we can see. NTOP can accept the Parasolid, SolidWorks file format, NX format, Creo format. In future it may accept other formats also. So it can accept the step format also, okay. We call actually in general as a like mechanical or CAD designer, you need to know the like step file, we call it as a universal file format. Why we are calling this as the universal file format, any idea? Universal file format we can say like okay, any idea?
Export anywhere.
Suppose I will tell you the example. You have designed some file like some glass water bottle or something, you have designed in the SolidWorks format, SolidWorks, okay, and your customer or your student may ask that they just want a viewing purpose. Editing purpose means you need that software only, but for the viewing purpose your customer may ask, or your student or some other may ask, your student may design and you have asked, but you don't have the SolidWorks software, you have some other software, Creo or something, because you might know that software, you have some other software, but you have designed a SolidWorks software, you have Creo software and you want to see the file, we cannot able to see the SolidWorks file format. So we need to ask the step or IGS format, so that the person can easily see the format, okay. Any software can accept the file format, that is why we call it a universal file, okay. So this type of file format is accepted, okay. So the middle volume is the middle body, okay, middle. So unit cell means here previously we have kept the graph unit cell, right, now we will keep the TPMS unit cell, okay. Just double press on it. Here you can see TPMS unit cell, wall TPMS unit cell. Wall means it has a thickness, okay. Shell type something, shell has a thickness, right. Again we can see xyroid, quartz, diamond, these things we can see. We can apply the xyroid. Again the same thing, like you increase in the unit cell, increase in the thickness, everywhere the what is the happen to weight, that is same, okay. You can take 10 or 10 by 10 initially. So the thickness it is asking, I can take 2. So this is not a good, okay, we can take the 3, this thickness we can reduce 0.5, yeah, or otherwise 0.8. See we are getting like this, right. So this is the our lattice body and this is the left body, this is the right body, but the problem with this means these 3 are the separate bodies. Forget, like yesterday some guy asked, if you want to do the analysis means I can't do, like doing the analysis it will easily separate, because the 3 are separate bodies. In terms of manufacturing also I will say, if you are exporting like this, you will print it with the separate bodies only. Again you need to stick with the Fevicol or something, that is the difficult, right. So we can stitch it here only using the Boolean operations, okay. So we need to combine these 3 bodies. Middle one is the lattice body, left body, right body. We need to combine these 3 bodies, right. So we will use the Boolean union, okay. Boolean union, okay. So we have 3 bodies, right. Here only 2 bodies are there. So press plus and I will simply drag this one, and I forgot, like I told you, right, there is one more method, is the second method, how to identify which body I should place. The right thing to place in the right place, right. That is the one is important. You can see here the second one is the iconic method, okay. Icon means you can see here, icons is there, right. The same icon where it is there you can find it. The same icons are there here also, means that it is accepting those type of bodies, okay. See, icon is there, the same is there. So if I keep it here, it will place it easily, okay. And the thing is, all the implicit bodies are in the green color, all the lattice body in this color, and the imported CAD bodies are in the yellow color. That is also recognition method, color recognition, color coding method, okay. So I can keep this one, okay. it will accept, drag this, and this is also implicit body. Once we are converting into, I told you right, implicit body, once we are converting into anything means that will be also implicit body. So this is also implicit body, I can keep this and write this one. Okay, now I combine. I will show you one more time this one. Lattice, right? Okay. See, here we have seen the gap, right? Means that is not combined. There is a small tolerance gap is there. Suppose if I am pressing a I, and here you can see we won't see a gap. That is a single body, right? So if I press this here, this is selecting as a single body. If I press here, this is selecting as a 3 different bodies, right? So this is how you can apply the thing, and you can explore the other lattices here also, gyroid or something you can explore here. Okay, that is how you can fix it. This is the CAD body, but what if there is a STL body? Means STL means stereolithography, means tessellation, triangles is there, right? Okay. So we will quickly wind up that bone or something, so that we can go for the break. Okay. So I will take the other one. Okay, one example I will tell. Which one I should take? Brake pedal or bone. Okay. No, brake pedal means again CAD body only. Bone means STL body. CAD body we have already explored, right? The same thing. So bone I can take. Okay. Same thing. Bone means in between this is the bone, right? In between I am applying a lattice, but there is no faces there to select. Here we can easily select the faces, right? So I can take this. Okay. See, this is a meshed file, you can see here. See, as I told you, right, STL is all about the tessellation, triangles. You cannot able to find any square type of something. This is all about triangles only. First we will convert this into mesh body into implicit body, then only we can play anything. Okay. So convert here, type implicit or something. We can see here, this is not implicit body, this is from implicit body from mesh. From mesh only we are getting implicit. So I will take that. You can see the icon again. I told you, right, icons. So this type of icon we can find it here. Okay, I can keep this here. Okay, see, this is converting. Now the real problem is that previously we have separated 2 body in the CAD geometry, right, like the middle portion, these thing. But here the problem is the bone is the scanned one, means STL file. So we cannot able to select the faces. We need to use the Boolean operations here. Okay. So this is your bone. I want to cut it from here. In this portion I want to apply the lattice. So I will cut that bone. So I will use the Boolean subtract. First I will cut it, right? Boolean subtract. The primary body is this one. Primary body means in this body only we are applying. Okay. Boolean subtract, I am subtracting with respect to planes. The like plane reference planes is there, right? With respect to reference planes I am taking. Okay. So I need to separate this body, I need to extract the middle body. So how many cuts I should give? Extract the middle body? 2 cuts. Here 1 cut, here 1 cut, right? So 2 planes I need, right? Okay. So I will press this, so I can get the 2 planes. I can press plane or reference plane. I can use the plane from normal. See, your plane is here now. Okay. You can change the view. Your plane is here. I will drag this here to in our required place. Here I want to drag, and this position you don't need because reference plane is the infinite geometry. That is a like a reference geometry that doesn't have dimensions. Okay. So one more plane I will take, copy this, and I will use the same thing. Like I will change the position here. It already cut. Okay. This is the body, right? Okay. This is the plane. This is the plane, second plane. Okay. So this is the portion. Okay. Just to see the identify, we can put it here. So in this middle portion, I need to get it. Okay. This middle portion I need to get. Suppose we will see whether cutting is correct process or not, we will see. See, we are getting this one, means we need to change the plane direction, then we can get the correct one. So 0 0 1 is there, right? This one we can change. This I can press -1. Both are in the same direction. This here in this direction, you can see. So I will keep -1. Let's see. Okay, this I will keep +1 and this I will keep -1. Yeah, I am getting this one, right? So my intention is to apply the lattice on this body again. Yeah, one more thing, like what about the other two portions? We need to combine later, right? The other two portions also we need to get it right. So we need to, which operation we need? Boolean union is there. Union means combine. We already did the subtraction. Then which operation? There is one more operation, Boolean intersect. Common body we need to extract, right? That we will extract it, okay? So Boolean intersect we can extract. So the original body is the bone one, okay? This one, bone. Okay, I will rename it bone. Middle, this I can keep it as a bone middle. Just for the future reference I kept that. So bone I will use. The common body it will identify. Bone middle, okay. See, we are good. Sorry. Oh, sorry. We need to subtract it actually. The common body we need to subtract that body. Common body we are getting, right? So Boolean subtract we need to do. Subtract from the original body we need to subtract. The common body we are getting here. So this one I can keep it here, primary body. This middle one I can keep it here, okay. So we are getting this one, right? This is our non-design space body. We don't want to apply the lattice here. So I can apply the lattice here, middle body, okay. So bone middle I can keep. 2 minutes we can complete it, okay. So unit cell set, wall TPMS unit cell I can keep, gyroid. Okay, distant diamond I can keep, and some 10 by 10 by 10 I can keep, and the approximate thickness 2 mm I can keep. See, we are getting this one, right? And if you want to see the sectional view, you can see the sectional view, okay, how the structure is changing, okay, how the property bone structure is changing, okay. And we need to combine these two bodies, right? These are the separate bodies. So the combination of body, this thing. So we can union this one, okay. This body, lattice body, and this body. Two bodies are there. So this is how we can get it. Again, we can convert this into STL body, but the processing time will get more. That's why I am not converting here. That STL body you can use it for manufacturing. That is how we can use the topology. And weight saving, last thing, this one, then we can wind up. Weight saving we will see. Lightweighted body means this one, right? Combined body, bone final. Can keep this as, okay. So this one, lightweighted body, bone final, okay. This I will delete. And the original body is this one, bone, our primary body, right? So bone we can keep, okay. So how much weight is reducing means you can see. See, 13% weight we have reduced with this design, and if you want to reduce further means you can change the parameters and all those things, okay. Yeah, that's all about the topology and how to generate the lattice structures and all those things. We took the quickly wind up we took the two examples. One is like a lattice tensile sample, bone sample, and now we are applying for the cube sample. And the main thing is that 2D sketches we cannot do. That sketches and everything we can do it in the SolidWorks, and we can use it for use the 3D models. Like if you have a 3D model, original 3D models is there, we can play with NTOP, okay. We cannot able to design everything in the NTOP, like the chairs and everything, water bottles, that we cannot do. That all needed 2D sketches, okay. So original bodies if we have, we can play with that, okay. Yeah, that's all about it. Thank you.
Mechanisms. Whatever may be the feeding mechanisms that will melt and deposit to form the beads. That beads is multiple layers like deposition is taking place to fabricate your components. Like three-dimensional, whatever the structure we are defined, according to our path planning, it is going to be fabricated and all. Right? If you observe here, this is component, how heat accumulation is accumulating over the build of the layers. When you are depositing, keep on depositing, because each layer is going to solidify quickly, rapid solidification takes place, and then the next layer again we are adding, again heat accumulation is taking place. Because of this, we are having either maybe thermal deformations, or maybe peel off, or maybe structural deformation, and also we are having lot of residual stresses, right? But in numerical, what we can able to analyze? Because of solidification we will be get different microstructures also, that is another aspects. But in numerical we can able to identify how much deformation is going to take place, means how we can able to control the heat. That is what, by correlating our the laser power, scan speed, and as well as the powder feed rates. With respect to that, we can able to correlate how much the heat has to be supplied to melt the required amount of the powders, to minimize the solidification and to control the solidifications. That will affect the minimizing your deformation of the components, or as well as delamination to minimize the residual stress also. Even if you are clamping at one end and if you are not clamping at another end, if you keep on developing a single layers, what will happen? It will overhang and it will deform in the another end. It will become like a concave like structures and all. Why this is happening? Because heat accumulation is another end is freely, it is not supported, it is freely supported. That is why the deformation, more amount of stresses are deforming and to deform the part and all. These things and all we can able to numerically model it. However, the heat source is flowing, and as well as where the more amount of resources is going to cause. And even if you want to make multi materials, bimetallic materials, because some materials are not easy to join, because that may be thermal deformation, quotient of thermal expansion, or maybe solubility of the materials, because one material may not be soluble in another, how much percentage, that is also another issues. And also it may form some kind of intermetallic materials also. But all these things, intermetallics we cannot able to identify, but we can able to identify how much thermal stresses, Warmth stresses are going to generate between joining of these two materials. And this technology is completely we are available with welding. Already numerical, so many solvers has used to deform 3D ANSYS. So many welding models are there. With that same kind of welding models, now they adapted in the ANSYS as well as ANSYS additive. We can use ANSYS additive, we can use COMSOL, or we can use ABAQUS. There are like this so many number of softwares are there. With that softwares we can do perform the required functions. Means how we have to perform, like my one of my master student in the last year, he has performed this experiment. We wanted to fabricate like thin wall fabrications. As I showed you in the video, it will accumulating heat. But for the single layer, how solidification is taking place, and if I go for the multiple layers, how heat accumulation is taking place, and what about the stresses at the different locations. These things we can able to understand by numerically. This will give some the idea of in what range we need to choose the process conditions for fabricating our component. Directly we don't know how the melting is taking place, how your solidification is taking place, what is the process conditions, process window I need to set for melting aluminum or titanium or stainless steel. That window can be minimized by your numerical modeling. That what will give an idea in what process range I need to select the power or the scan speed and all. That's what he has performed. With that, if you see the in the numerical modeling, we have pre-processing, solver and as well as post processing. In the pre-processor we will define, because in numerical modeling we need to define either geometry or number of elements, how the elements birth and death we has to be taking place. All these things has to be defined. That is what we are doing pre-processing. And in the solver we are importing what kind of meshes, and as well as we need to define what is the solvers, and as well as we need to give the boundary conditions. What is the boundary conditions for that? Then we can able to understand post processing after simulating what are the data we are going to get it from the simulation aspect. That is what we can do in the post processing aspects. If you see in the pre processing, this is what done in the ANSYS. With that we can able to define. Here we have defined with some kind of a simple 3-4 layers of modeling aspect in the ANSYS additive and all. With that we have created a model in our any kind of CATIA or ProE or even Creo softwares and all. Even you can use SolidWorks. That model was imported here, and after that defining model we have used simulating solver. That is what ANSYS simulating solver, and we have given a governing equations, because how the heat transfer has to be taken care, how conduction is taking place and convection is taking place, and these are all the governing equations for our static structural materials. These things we have defined, and also as well as we need to define material properties, the thermal properties, geometric models, and as well as material properties. Means we need to define what thermal conductivity of that materials, what is the density of that materials, and what is the physical properties, what is the melting point and as well as boiling point of that materials. Whether we can use titanium, stainless steel, for all those things we need to enter all the physical properties of that materials. That how we are feeding that data into this your ANSYS additives and all. With that we have fed all the process things, and we have defined all the material properties in our ANSYS additive things, and then we have given the process conditions for our, how, what is the laser beam we are using, how much power, what is the travel speed, how much powder we are feeding, and what is the wall height, and what is the focus radius, that is what the laser radius or the beam radius. That things we have to feed into our system, then we can able to perform our post processings. These are the results we are going to get it after post processings. That is pre processing, solver, then post processing. With that we can able to define. If you see, these are all the data we have got, but what we are getting with this, if you see in this, what we are getting in this, we are getting temperatures versus time. With respect to time, how your solidification is taking place, this is what the cooling curves means. If you see at 0 seconds, your temperature is almost 1500. It's actually a multiply by 10, 1500 degrees centigrade. That's what for the stainless steel we have tried, and it will come down within a 40 seconds. Means that is not will come down, it will zigzag like manner, it will come down in a slowly cooling rate. That is because in 40 seconds entire your 1500 to almost room temperature will come down. That much rapid solidification is going to take place. That is what 10 power 4 to 10 power 5 Kelvin per second solidification is taking place in your DD process. These things we can able to analyze. That's what we have defined our substrate models, and as well as your deposition layers. And for first layer we need to define, because the element has to grow and it has to die. That is what we are defining. This is called element birth technique, birth and death technique, that we are defined, and we can able to solve these things. Even you can do for single bits or multiple bits or entire component also we can able to do those things. That how geometry we are importing, like that geometry we need to define, and we have to give the constant and material properties, and with these you can able to get temperature distribution at what locations with respect to the area or the substrate, how the temperature distribution is taking place. And with these we can able to get residual stresses at different locations, how your residual stresses are going to be defined. Those things you can able to get it from your modeling. If you see in this animation here, this is what the substrate, and next we are defining the first layer. means you can able to define for each element how it is deposition and solving is taking place. With that, for the single layer we got the results of your temperature distribution and as well as the stresses, how one measure stresses are generating in the fabricated parts. And if you go for multiple layers as well as for the multiple layers, or if you go for your different kind of materials and all, if you see here in the first layer it was deposited, then if you go for the second layer, this is what that is how we are defining our deposition strategies or the scan paths and all. If you compare that, the first what single layer in the previous slide and in the second slide, how much temperature distribution and thermal deformation has taken place. In the first layer only we can accumulating this much more amount of heat in the left side, because that is at the end of your point. But now if you see the two layers was deposited, how much deformation has taken place and as well as temperature distributions. This is what we can able to define and you can able to simulate and you can able to do in our numerical modeling, and then we can able to compare with our respect to our physical demonstration of LDD experiment or the PBF experiments, right? And if you see, this is what we have done for some multi-materials, because we are facing lot of issues. Is this because of only the precipitates or the different intermetallic formations, or also maybe because of the temperature distributions or coefficient of thermal expansions? There will be a solubility issues also, but we have not taken care just to identify is it only because of these things and all. How much stresses, how much temperature distribution is taking place. For that we have taken a substrate is titanium and we have deposited after that a titanium, then over we have deposited a stainless steel. Then we have come across this is what the cooling curves with respect to this bimetallic materials, and then we also simulated how much temperature distribution residual stresses is going to taking place with respect to the deposition of the models and all. And then we have come across that at the interface between your bimetallics there are a lot of amount of heat is generating and delamination is taking place between your fabrication of the multiple materials and all. These things we have correlated with your experimental data and we have come across some kind of a solution what perform we need to do further to solve these kind of issues. We can control the substrate temperature or we need to do any other kind of experiments. This is what we have performed with our laser DD experimentations with ANSYS additive solutions. And also one of my students also working with ABAQUS to simulate your powder bed fusion aspects with respect to the aluminum and other materials. He will show how to use our ABAQUS, your student version ABAQUS, and if you have any license version you can also use that. Okay, and he will train you how to define the models, how you can able to import that models, and how we have to define this element bar techniques for single models or for the multiple nanometers. You can apply same, but only thing we need to have the high kind of systems, servers or as well as workstations are required to perform. Otherwise it will take even months together to perform the experimentations to numerical simulations and all. Okay. Okay.
Only for this student version based. For other things we need to go for the licensed version. Here there will be some restrictions that the total nodes within the deposition should be less than 1000. If it is more than 1000 it will not be acceptable. So we just need to go for like the meshing size and everything will be somewhat higher size. Initially when you can download it from the Dassault systems, that will be called as a website. In that you need to mail the company for the information. They will give you the license that you can use it for your student version with your institute email ID. Then here we will be having different options for just to go for the simulation. If you just see the module, we can have the part initially just like to create the geometry of the part, whatever the bead or something like a multi-layer deposition, everything. And then in the property option you just you need to give the what are the materials. If you have seen here, if you already defined the materials earlier, then it will be fine. Otherwise we can give it in a something like if it is a stainless steel, aluminum, according to depends on how you are working, where and what you are working on it. So from here, if you just go to the general options, it will having some density. Then give us some what will be the values and all. In the mechanical, you can see multiple options like elasticity, plasticity, and also the expansion, deformation, plasticity. And then when it comes to thermal conductivity, specificity and everything. So uh, once you define the materials, here you will be having a option, I mean like further we can go into the in-depth. And then third option will be assembly. If you have it in a single layer, then it will be there is no need to go for the assembly. Then if it is a multi-layer, then we need to choose the multiple I mean like assembly for multiple adding the each 3 layers, 4 layers, whatever it may be, number of layers. And then step, this is step is main thing, like how we are going to simulate, what are the conditions you are going to give and everything, like whether it is a statistical heat transfer, those type of conditions. So someone will be only focusing, I mean like in abacus is accessible for everything. It will come to am and normal statistical analysis and everything. So if you want to only focus on the statistical data, like what will be the stresses and the deformation during the deposition, then you can only concentrate on that. If you want to be see how the heat distribution will be happening after deposition, then you can just go for the choose the option like a heat transfer. Then we have the interaction will comes in multiple layers, because we in a single layer we are not going to have any interaction between other element. And then load will be some like it will be the boundary conditions which you are going to give it, whatever the I mean like how you are going to give the pressure and load equal distribution. Mesh, as we have know the size of the element will be getting reduced. And then job is just like we are assigning the job, so it will simulate and give the product. And visualization sketch, everything will be related with the final output. So first we need to go for the option. Here you can see, first we need to save the data. Initially we need to create a file and have to save the data. Here we have the option called set directory. If you just click on this, it will give you the file like stores where you are going to store it. So I just want to keep it in somewhere, something like I will create a one folder. Here it will called copy this and paste it here. So it will go to the directory. So whatever the data you are going to have it, it will be stored in that. See, it was already there. If you go to here, that abacus, the folder which we have saved it. So whatever that simulation you are going to perform, that will be going to store in that that same folder. Then first thing is like we are going to keep a part. First we need to create a geometry. We will first deposit one single bit, like we will see the statistical analysis, and then we can go for that. Here we have the first go to the option like create part. Here it automatically it will ask whether it is a 3D planar, deform, 2D planar and everything, and we are going to work on the extrusion. So we just want to extrude the part. Approximation size of the interface what you are going to want to be take, like if it is a 20 mm, 200 mm, according to that you can get. Here we are not going to give any units for the modeling, but in ourselves we are going to assume that we are taking the length in meters and time in seconds and pressure in bars, pascals. That's what. So here I just want to go for something like 200 mm length. So I will just go with the 2.2. If you just click on the continue, it will give you the interface regarding the part geometry. For that you can go for the whatever the options you want to go for, whether it is a line or circle and rectangular, anything. We are going to work on the rectangular. We are creating a part. Just click on this. Either you can draw it here or something like you can give the options, like the what is the coordinates for the x and y. So I just want to give point 1 which in which we are going to have a point 2 200 mm length, so I just want to only have the 100 mm length, so comma point 1, just click on enter, and then it will ask you the origin point that we are going to give it as a 0 comma 0, then click on enter. So click on done, then we are going to have it a extrusion for 500 mm length, the total length will be, so point 0.5 I will say. So this is what you are going to get, normal bead for the example is you just want to see. So once we create the geometry, go to the option called property, in which you are going to give the materials as we have already discussed. This is we are working on the statistical distribution, then we just want to go for the density. Anything you can give something like 8100, it will be in kg per mm cube. Then go to mechanical elasticity. We don't want to make it complicated, so we just go with the initial things. Elastic Young's modulus something like a 200 e power 9, if it comes to 200 gigapascal. Then Poisson's ratio we mostly consider 0.3, then click on OK. So it will the property, I mean like we have provided the initial data. Then go to the section, we are going to create this part will as a section, so it will automatically give you the options. Go to the continue and then click on OK, but we need to assign the section to this part, that you are going to get it from here. Assign the section, it will ask you the whether the sketch which we are going to we already produced, that whether it will be or not. Then click on OK. Sorry, if you just click on OK, it will turn into green. That means we have assigned the material for that respective geometry. Then if you want to edit the material, you can go to option here. Otherwise, if you want to create another material, it will comes to material 2 or something. We are not going to have it anything, we already created one material, that is fine. That's material which is of a solid and homogeneous, which we have already taken it. Then now we are going for assembly, but here in that case just go with a normal part, just click on OK, because we are having only one part. If it is a multiple, then we want to we need to focus more on the assembly. Then go to step option here, which we are going to work on it is a statistical analysis. So just go to this, then create step. First thing, it will ask you the statistical or general or heat transfer, anything that explicit dynamics, depends on what you want to perform on your work. So here we are just taking care of only statistical. Then go to continue. It will ask you the options like what are the time period and incrementation, what is the different I mean like a number of steps and everything. So here if you just see LGOM, if you can see here NLGOM, that depends on like normally it will default it will take off in an option like choose option like off, but the thing is like sometimes we have a overhangs which is of more than I mean like large deformations. If it is a straight, then it will be we are going to keep the load in a perpendicular to the, this exact load, but sometimes it will deform, in which some more into the lower edge will be in the inside and this one. In that case, if you keep it this load in a perpendicular, but it will not have, it will be having some angle, it will not be straight exact perpendicular. In that case, we are going to give this option, I mean like the load should be in this perpendicular direction. In that case, that will go for the large simulations. That will help in, if you click on on option, I mean like if you choose this LGOM as an on, then it will help us in whatever the overhangs it will be there, it will automatically take. Then time period, we are just going to have it a 1 for whatever the I mean like according to your things, you just need to go for that. And initial for example like I just want to be having a 10 steps, then I want to differentiate what is the initial length and point 1, and then maximum. These are the number of increments for the first deposition to end. We just want to be, it should be in a large number, we can go for that. Then give a something like a 1 lakh we are going to give it. In other options you can go for, just click on OK. It was already there, we have to we have already defined. Then go to the create output field option. It will ask you to go for step 1. Here you want to choose on what you are going to focus, like whether it is a thermal or stresses and everything. Since we have already chosen as a statistical analysis, we just want to only concentrate on the deformation and stresses and everything. Otherwise if you already have, I mean like initial conditions what you have chosen, that if you select here the pre-selected defaults, if you can see this option, that will automatically choose the stresses here. If you can see displacement, stresses and everything. If you don't want to be, you want to give it an exact thing what you want to be, then you can choose other things. Here whatever the stresses, what stresses they have chosen, like stress components and invariants, not all, and then strain, you can see plastic strain magnitude and logarithmic strain components and displacement in this way. Just click on OK. Here if you say hey, yeah, same thing, if you just want to edit it again, you can go for the output option. Then we just want to go for the interaction, but here we don't have any interaction, so go to the next option called load. Here we are going to give the boundary conditions. See it here, we just want to see mechanical category, we are working on mechanical, and this is a pressure, we want to give the pressure, that is in a Pascal. Go for continue. It will ask you on which surface, on which direction you want to provide the pressure. I will select one end so that other end will be automatically. Go to the just click on done. It will ask you the magnitude, how much you want to give or something like that. Approximately whatever the amount you can give. If you have an exact amount, then you can go for that. I will just give a e-power 5 something. Click on OK. So if you can see here, the scroll button, if you move forward then it will zoom out. If you scroll inward then it will zoom in. That is okay. Here you can see, sorry, now we are going to give the create boundary condition, that we are just checking it is a symmetry, the sample is in a symmetry. Then go to continue. Then it will ask you on which side. We just want to be give it an opposite to which we have given the pressure. So I will choose this area and click on this, and here how you are going to give the load, whether it is an equally distributed or you want to be particularly in a single direction. Then normally we will go for the e-cast tree, that will be conditions in all the directions. Since we have chosen a symmetry, click on OK. It will give you the all pressure in this direction. Sorry. Now we have provided the boundary conditions, and then go to the option mesh. Here if you see the seed part instance, sorry, we are just see, we just want to give it in a single part, then it will automatically choose the number of if the more number of layers, it will automatically take the conditions which you have provided for single option in the seed zone. But here we just go for the option called part, then give the mesh. Here it will ask the global size. By default we will take it less because it is a limited version. Then click on apply, OK. Then here it will give you the mesh part. It will ask whether okay to mesh or not. Then we will say yes. So it automatically given the mesh. And if you want to verify how much nodes and elements, then if you see this option icon, you can on the top just click on this. It will ask you which option it should be mesh. If you see it here, number of nodes are 132, number of elements are 50. Okay. If you number of nodes and elements, particularly someone wants to keep the data in their papers and they would just want to give a number, what are the elements they have distributed, then in that case, for regarding the details, you can go to that option. We have provided the mesh. Now go to the, we are not going to go any optimization, we are just going with a job that we are going to give it, assigning the job, create a job that is nothing but we are giving this result. Just click on OK. Here if you see it here, job manager, in that here it will ask you to submit the data, whatever the property you have presented till now, it will ask you to submit the data. If you just submit, see it was running here. If you want to monitor, yeah, see we already given it from the incremental from point 1 to 1. So how it was automatically distributed, like we have it would take in 6 increment size, and equally it was take the number of time step and everything, and what are the time in within the seconds, uh, from point 1 to 1 it have taken it. Then if you go to that option called results, see here we just wanted to be in counter, how it was distributed here. U is a magnitude, that is a stress. If you wanted to be if you can see that I mean like how the distribution is happening during this after the deposition. If you want to make it in for like the frame rate should be less, then go to the option like animation options, click OK, then it will slowly distribute it. And most properly we don't want all, I mean in the while keeping it in the publications, we don't want all this data. In that case, just go to this viewport, yeah. Here we are going to have it in a viewport annotation options. Here it will ask you what are the data you want to keep, whether it is only tried or less than anything. We don't want all the extra data, so we will just remove it. Then click apply, so it will already removed. Then OK, and then go to this option, it will ask you, sorry, it should be of a continuous, we don't want to be it something like a disturbed, it will get smooth. Click OK. Now this, Here you can see the legend options, like we, if you don't want, mostly we will go for a scientific, whatever the format here, if you can see. Otherwise in engineering we will just apply, it will go to in engineering data, how you are going to define your data, and a number of decimals, like up to what you want to keep, and this font style, everything you can change. There you can save the image. Actually one option will be there. Yeah, here you can save the file by taking it as a print. It will ask you all ports are current viewport, and black and white are color. Mostly you can go for the PNG, it will better it option. Choose the option where you have saved it, click OK, then save. So it have taken the background as a black, that you can change. And animation also you can save it as a save. Number of frames you can go for that. Apply. It should be animate, I mean like it should run the animation during while saving the option. Sorry. So frames are less, so it is going very quickly. According to your data requirement, you can go for that, whether it is a stress magnitude or deformation and everything. So now we will see. We will see more number of layers. In the same way, you just need to give that set work data. Sorry, it will have taken it. I'm just creating new folder. Uh, Multi-layer. Copy this location. Keep it here. Just click OK. Then same way we are going to give the part. Go to the option. We already have the point size. Go for continue. Then click on enter, then go for 0, 0. Initial steps will be common. Okay. same initial steps will be common. Then go to property, we just want to add a material, new one, density how much you want to take, 7800 suppose. Go to elasticity, 250 gigapascal if you say. Sorry, Poisson's ratio will be 3. Then go to plastic, it will ask you the yield stress how much they want to give. I can say 20 megapascal, e power 5. Plastic strain, we don't want to involve the strain rate, so we will just say okay, 0. And here we have the option like use strain rate dependent data, use temperature dependent data. If you click on this, it will ask you the temperature, like whether it is in at room temperature, what will be the values at other temperatures, depends on the on what temperature you're working on. Someone will go for 100, 200 room temperature and everything. If you don't want to be more complicated, then just unchoose this option. Then we have the expansion a little bit, we can say 200 at least. Then I just want to give the thermal conductivity, suppose 30. Specific heat is of 500. Then according to the data on which material you're working on, everything you can go for that option. Just click on OK. We have assigned that property. Then I just say sections, same thing, I just say OK. Go to that option, choose this body, done. So it have chosen the I mean like a material was assigned to this body, if you can see. Now main thing is like assembly. Yeah, now we are going to have the multiple layers, so we need to add them layer by layer. So this one first, if you see this option create instance, then whatever the part you have already created, it will create generate one more, I mean like a number of more parts, what are you going to take it. If you just click on OK, it was generated, that you can see it here, assembly part 1. And one more time, suppose we are going to check for 3 options, I mean like 3 layers. Again we will click on this, and this will be dependent on each material, I mean like you have to choose the instance type should be on a dependent, because each layer will be dependent on an already deposited layer. In that case, one more time click OK. So here we have seen part 1 2, one more time, because 3 layers. That now in order to get all the things into together, you just choose the option like a translate instance. It will, if you can see here, the axis origin point XYZ, we will say it will ask the select the instance to translate. First point we will choose this, done. If you click on this, then another layer going to be attached here, whatever the layer you are already created. Then click OK, select enter, so you can see 2 layers it was there. And then one more time we will say OK, and we choose this second layer, so other layer will be I mean like assembled on top of the second. Click on done, choose this point. Otherwise, if you know the exact coordinators, you can go for that. Then we have chosen this origin point, then click on again enter, just click OK. Sorry, something it got a mistake. Just a minute. Okay, part 1 is not there. It is moving in opposite direction. So just wait. Now we'll first create the instance part 1. Okay, suppose we're going to work on 2 layers at least. Now we want to see the interaction between these two. We have created assembly, then go to the step option, go to initial. We will work on the heat transfer, go to the continue. This is a transient, and give the time period how much you want to give, something like I will give some random value. Incrementation it will automatically take from here to here, and 1 lakh suppose. Okay, and if you go to here, this one rename, we will just it as a, we will choose it as a heat one, like heating one. Now one more we will create, and we will say it is a cooling one, that also same. In that how much you are going to give a time period, how much time you need to go for seconds, that is I will just randomly give 40. Here also same thing, click on OK. We have given the heating one and the cooling one. In the same way, one more create, because we have two layers, so one more time we have to create, and it will be saying a heating 2. Each layer should be give the heat source, and we need to cool it down. Same thing we need to repeat. But the problem is in that case, if you have a more number of layers, it's better to go for using some code, Python codes, or those things will be helpful for you. Just click OK, and one more thing we will create, that's we will call it as a cooling 2, continue 40. Just click on OK. So we have given that all the time periods for this. If you can see it here, it was all created and all these are propagated. And go to the edit option. Here we are going to give the option like which one we are working on. Since it is a heat transfer, it was automatically pre-selected defaults, it will take thermal option. So we are working, we're going to check the nodal temperature, heat flux vector, and reaction fluxes, whatever the things it will be. Just click OK, close this. So we have given it. Now we have the interaction things here. We don't know whether the whatever the layers, if you are seeing here, it may have some gaps and all, so we should be having interaction between these two layers. So whatever the temperature or heat distribution comes from here, it should be translated through this upper layers. In that case, if you can see here, we have option creator. Since this is working on cells, just we will say this bottom layer we are removing, because it should be having some gap, so that we can choose the interfaces of those two. We will just say click on remove. It was removed the bottom layer. So go to dismiss. Here if you can see, create portal, not this. If you can see here, constraint Taiwan, continue, it will ask you the on which region you want to choose the like the interface between. So this is the top layer, we want to be the bottom surface of the top layer and the top surface of the bottom layer. In that case, I will choose the option surface. I will just rotate. I will choose this surface, it was highlighted, and then done. Another surface we just want to choose, because on the top surface of the bottom layer here, if you just invert the display, it will ask you to bottom one. I will choose this option, surface. I have chosen this one. So it will ask you any constraints if you want to modify it. If you can click on OK, see the interaction between these two, that you can see in the full body. You have already taken it. So interaction was created. Now we will go to load. Whatever the load we are going to give, first the boundary conditions. In this case we are going to give the since we are working on the heat transfer, we will just give it in a heat flux. Go to thermal, here we just need to go for the heating one. Go to continue. It will ask you on which surface. We will say this one. Sorry, all things. So that load will be convection. The heat will be distributed all around the surfaces. So what is the magnitude? You can give it some value, some 20 or 1 power e power 5, anything. Click and OK. So heat was distributed, we have given the loading conditions of heat convection in the form of convection all the surfaces. Here you going to create a boundary condition. Okay, not required. Go to this option, edit. We have given the flux. Just a minute. So but we forgot to give the interaction. Here if you can see, not this one, it will ask you to surface film condition. This will give you the heat condition. Now you need to choose all the things. It will ask you film coefficient, how much it will be, 15, and temperature, how much it will be. We are working on the room temperature first. Click on OK. In the load, what will happen is like, now what is the heat flux we are going to give it? It again depends on the formula called Q equals to absorption coefficient and the laser power which you are working on it, divided by some rate of deposition and also the travel speed, scan speed. That all the values we should need to calculate according to the what is the height of the deposition and everything. For example, I have chosen different conditions like a 200 watt and absorption coefficient as a 0.25, and interaction time is of 120 seconds, and the scan speed will be 1 meter per second. In that case, I have calculated the heat flux, and then so here we need to give the heat flux as a something like, if you calculate that, you will get option like 0.04 something e power 14, whatever the travel speed and everything you are going to search. Click on this OK, and then do it for all the things. One more same repetition for heating 2 also. Go to continue, and this one choose the option, and same value you are going to give it. Click OK. Now we have given the heat flux for both the things, heating 1 and heating 2. Now we have given the boundary conditions. Now we just need to mesh it. In this case, in assembly it won't take, but because of we have the limited edition, in that case we just need to go for part. It will choose the single part, same thing like seed parts which we have given it, it will approximate global size will be 0.01 or something like, if you can go for more size it won't come, because of more, if number of nodes if it is greater than 1000 it won't work. So just choose the better default option which it was suggested for initial learning conditions. This is everything. If you have a licensed version you can work on the more number of fine mesh, that's what you can say. Just click on OK. It was done, and we will see the C part. It was meshed. Meshing was completed for the single one. If you choose the assembly, then it was automatically it will take for all the nodes, because we have already copied it from each one. Again we have the given size, and what is the element type you want to give it. If it is a transient and these things, we just want to given the assign which type of mesh element. Here you can see it will automatically and by default it will give you the 3D stress, but we want to work on heat transfer. Now we are working on, so just click on OK. So this element type will be done for both the things. Now we are going to give them a job, sorry, create a job, continue. We will just click OK, go for this option, submit. It will ask you the heating one, cooling one, everything. Just go for OK. It will register it, submitted. We can go for the result. Yeah, this is what you can see. Go to the thermal one. If you can see the bottom layer is how the temperature was got distributed. Slowly. And one more thing we forgot to give, that is a model change. The model change, like the first when the top layer is heating, I mean like a bottom layer is heating, top layer should will not be having any effect on that. But when the second is heating, the bottom it need to cool, and bottom will also have some effect on the like a heat effect, that we will give it in the interaction. Here if you can see this, not this, here you can say model change, that will give you the heat I mean like we are going to, like sir, as sir mentioned, it is a element birth and death in this way. Same thing we have given it is a MC1 model change. If you can say for the heating one, continue. It will ask you by default I mean like it will ask you the region option. I have chosen the bottom region, click on OK. We are deactivating in this step, and we will reactivate further once. I will just say click OK. In the same way you need to give the model change for second heating too. MC2, continue. It will ask you the region, choose the option, done. We have chosen it. Here if you go to here, you can see what are the inputs we have given. Yeah, model MC1 and MC2. Here it was already I mean like first heating one for the bottom layer, heating one is created, but doesn't have any effect on the top layer, because only we are working on the bottom layer. So in that case, go to option here, deactivate it again, and here, sorry, edit option, you will see we are going to reactivate this step here. So modified in the same way, this one also, edit option, we are reactivating it. Now it will modify according to that. So this will not have any effect on further layers. Click OK. Now again go to that job option. We already have the data, submitted it. Now we can see more increments because of the layers. It was running, wait. The frame rate will be slow, so it will take time. If you can see the difference, slowly it was happening. Contour options, continuous, we will apply. Same viewpoint, whatever the things you want to apply, and you can save the data and check for the magnitude what the things you want. If you have a licensed version, you can go for the multiple depositions and a more number of layers. Okay, thank you.